functions can be described lots of different ways. So far, we've been focusing on the formula for a function and using that to find the formula for the derivative function. But functions can also be given to us graphically. And so I want to start taking a look at the connection between the graph of a function and the graph of its derivative. So I've written up here on the board, using some of our new notation, this fact that we've derived a while ago, that the derivative of x squared is 2x. And so over here I've drawn two functions. The original function, y equals x squared, is just this parabola. Y prime equals 2x, that's the derivative function. And I want to take a look at how this graph actually gives me information about the behavior of this graph. If I just look at the graphs, they look very, very different. But if I think about what the derivative is telling me, the derivative is the slope of the tangent line. We're generalizing the notion of slope to functions that curve. And the slope, remember, answers for us two questions. Are we going up or down, and how steep are we? So, if I take a look at x squared, I can see we always read our functions left to right. So coming left to right, I'm coming down. Okay. And it looks like we come down until we hit the vertex, which happens to be at the origin. Now, if a function is going down, what does that tell me about the derivative? Well, if a line is going down, that tells me that the derivative is negative. And when I graph something negative, I'm graphing the region below the x-axis. I don't know how well this shading will show up, but my other colors are too dark. Okay. So you'll notice that when f is going down, the graph of f of x is negative. It is the graph of f prime of x is negative. It's below the x-axis. After we hit the vertex, the function turns. It changes direction so that now we're moving up. And you'll notice that to the right of the vertex, to the right of 0, my function is positive. My derivative function is positive. The graph lies above the x-axis. Okay, so up or down for the original function translates into positive or negative for the derivative. Now, if I look at this transition point, right here where we stop going down and start going up, we can't really be said to be doing either. Okay. So at that point, the derivative isn't positive and it's not negative because we're not going up, we're not going down. We're changing what we're doing. Well, that means that the derivative has to either be 0 or undefined. We've talked about this a little bit before. If I follow this, I kind of level out here. Looks like we've got a horizontal tangent at that low point, and you'll notice that on the graph of the derivative, we're at a value of 0 there. The other option, if this were a sharp corner, then the derivative would be undefined, and the graph would look a little bit different. But here, if it's a nice rounded change, then where we change from negative to positive, we do that by actually passing through 0. We don't jump over the x-axis, we pass through it. Okay, now if we look at steepness, remember that the steepness of a line affects the absolute value of its slope. Lines can go up or down, so they can have positive slopes or negative slopes, but the absolute value tells me how steep they are. And when the absolute value is big, we've got something steep. Now, since I'm putting the slopes of my tangent lines on the vertical axis here, I want to talk about where are my y values on this graph big? Where do they have a big absolute value? And that would be where they're either very high up or very low down. So there are sort of two steep zones that we have. If I've got values up here, those are positive and big numbers. That's saying that the graph is going up and it's steep. And that corresponds to what we've got over here, which is definitely going up and quite steep. Down here, we've got negative numbers that have a big absolute value. The fact that they're negative tells me that f is going down. The fact that the absolute value is big tells me that it's steep. Yup, definitely true. Okay. Now, not so steep is just going to mean that the absolute value of the derivative is close to 0. Okay. So not so steep is going to put us closer to the x-axis. Now, if I follow along here, we're very, very steep. As we move to the right, we get less steep until we hit 0. We're still not very steep, but we start getting steeper as we go up, and then we go back to steep. So if I follow this graph, we go from steep, but going down, still going down, but less steep, less steep, less steep. We level out at 0, where we have a horizontal tangent. Then we start going up, not so steep, but getting steeper. So the behavior of this function is encoded in the graph of its derivative. Now, if I just had this graph, and I was trying to sketch the derivative without having done the algebra to know that this is the correct formula, it might be hard for me to tell that that's an actual line. I might think that I had some curve that went from quadrant 3 to quadrant 1. And just eyeballing things, we're not going to be able to get a perfect graph. Okay. But what we're going to try to do in the next couple of videos is just take a look at some functions and try to sketch the derivative of that function to try to describe the behavior of the original function. We're not going to be expecting perfection, but we should be able to get graphs that are positive and negative at the right places and that are increasing or decreasing at the right places. Notice that down here, the fact that we're increasing means that we're going from steep to less steep. Once we pass through the origin, the fact that my line continues to increase has us going from not so steep to steep. But it's always encoding the behavior of the original function.